Okay, so I will take one last hour or maybe less of to discuss what kind of properties we will be computing starting Friday. And I will show you the results of the previous years concerning the article of Jonas Bolton, and you have to think about your own problems in your projects. Okay, so I think that the best is that to form pairs, okay, or maybe no, to work to work in trinoms, okay, and one binom. Maybe Rania, who has the advantage of already have done some calculations, she can be alone with someone, and the other to be three, okay, and you have to find and to do some bibliography, or maybe using what you've done in previous internships or what you've seen in different classes, and to see, oh, I would like to be able to reproduce by calculations this property or this scientific problem. Okay, you can already try to get an article and to see, okay, this is an experimental work, it's very interesting, I would like to see if it's possible to do the calculation of this. And you will construct a PowerPoint to present the results, and you will present in December, you will present the results to a jury, and it will be half of your evaluation for this class. The other half is the examen. Okay, so the written examination is in December. There will be no November evaluation, unfortunately. So I hope that we will have some time to discuss, to do some corrections. Okay, and you have to prepare an oral presentation of around 10 minutes concerning your own project. And we will start, and we'll try to get the input and to launch the calculation this Friday. So you have like 3 days to find your project.
Can I ask, like, one molecule, and I have several spectra, and I am very curious because I get some peaks, and I want to like make simulations from what parts of the molecule could I get them, and I have some questions that I want to find answers to.
Okay.
My project. Like, is it possible to do like that, or
yes? If it's an absorption spectra, how many atoms do you have in your molecule?
Actually, many of them.
So that means more than 30?
I have to count, but I suppose yes.
Okay, so the absorption spectra is not difficult to compute, and we will see how to understand the different bounds and excitations, and you can describe them later on as, oh, the electron goes from here to here, and okay, so this is not difficult. If the molecule is really big, it will just take some time. Okay?
I'm more interested actually in luminescence, like in excitation.
Okay, so the optimization of an excited state is one of the main objectives of this class. So in your group, you can propose there your project, okay? And I leave up to you the group selection, but please try to the ones that are weak in theoretical chemistry do not be together. Okay, try to mix the groups, that at least the ones that are not familiar with calculations can at least learn with members that already have done calculations. Okay?
Okay.
So yes, you will have to try to get a computational strategy, and many times the first step is the calculation of the ground state. In fact, it's our first objective, and it's not the first step in the calculation. So I've taken as an illustration of this problem, I've taken a part of an written examination that I've selected from 2 years ago. So we have a small molecule, ozone, O3, and depending on the position of the atom, the global energy is not the same. That means that you have the minimum in energy is this kind of molecule, okay, the one that you usually choose for O3, and you have a more triangular geometry that is stable, okay. It is another minima in energy. So for example, here you have the energy, and here you have the graph of the energy. But in reality, this graph is not one-dimensional. We use the intrinsic reaction coordinates to simplify the diagram, because it depends on the position of all the atoms. So it is a multi-variable property, and at least here you have the OO angle, for example, and OO distance. And if you have the correct angle, that means a large angle between 120 and a small distance, you have this kind of open shape, and is the most stable energy. You can have another minimum, that is a triangular interaction, okay, between the three. It's not the most stable, that means it's not the global minima, but it is a local minima. It's like a molecule that have different spatial conformation. That means that all the spatial conformations are minimums of energy, but one is more stable than the other. Depending on the energy barrier, you will have an equilibrium or only one of the two species. Okay, so if you have a high energy barrier, you can maybe see more than an equilibrium. You can be blocked in a cinetic, for example, conformation. That means if one of the two conformation is more rapidly produced in a kinetic approach, you can be stuck in what could not be the most stable conformation. That means, for example, diamond is not the most stable solid state of carbon, but the energy barrier to go from diamond to graphite is quite huge. So kinetically, diamond is stuck as diamond. Okay, and I think that the half time is around 50,000 years. Okay, so it's not eternal. So this is the potential energy surface. That means it is the energy of the geometry depending on your approximation. So what you want to do is you start with your molecule and you want to get to the global minimum. That means that better not start, for example, here. If you start near this compound, the second minimum, the optimization will lead to the first minima and maybe will be incapable to go to the global minima. So beware when you draw your molecule, okay, when you prepare your first geometry, your starting geometry, before optimization, try to make a geometry that is coherent, logical, that seems to be plausible, and chemically sound and reasonable. Okay? And if you are here, for example, you will get here. Oh, when I put my energy here, so if I can insert across, let me try something. Up.
Why we will stop on the first one? You said like we have to just start with the reasonable structures, but why can't we, with our calculations, go to the general minima? Why we can be stuck?
Yes,
on the first
perfect.
minima?
So good question. So I will try. I've bought a stylet, but I've never used it, and I'm sorry if it's doing some strange things. Okay, so let's change color. I see red. So let's see. Okay, no, why is it? I don't want to. I want to draw. Okay. But why? Yeah. Okay, so I need to practice before to be able to draw. So because usually this class I do it in the classroom, so I can draw a picture of. So I need an X insertion of text. X, maybe a smaller one. Okay, and let's start with the red. Okay, so your starting geometry, you start your geometry here. What the program will do is to start to minimize the energy for this geometry. So the first thing that he will do, he will minimize the energy. Up. Okay. That means it's a single point because there is only one geometry. Energy minimization. Up. Minimization. Okay, so if you start here, you will be here. You will try to. I wanted something that is. I want something that is purely vertical. Oh God. Okay. So when you have the minima of energy with this geometry, he will try to see what is the best approach to minimize changing the geometry. So he will look at the first derivative of the energy, and this is the direction of the best localization of the next minima. That means that he will try to go here in maybe in 1 or 2 steps. So he will see, okay, if I go in this direction, if I change my coordinates to display the atoms in this direction, I think that I will get a better energy. So let's change the color, because this is now really the optimization. So let's make it in green. Geometry change to get to their nearest minimum in green. So he will try to change the geometry. He will again optimize the geometry, the energy. And when he is here, he is in a global minima. That means that if he changes the geometry, he will always go up in energy. So the program, to be efficient, to work in a minimum number of geometry steps, it will not allow you to go and try to go up in energy to go down. The only time that he do that is when he's stuck and he doesn't manage to get a real minimum. That means he knows that the energy surface is quite flat, but it's not a real minimum. He will give himself some latitude to change the energy to go higher in order to maybe gain. But if you start here, the nearest local minima is this one. You will be in this geometry. So to get the global minima, you need to start around the geometry.
Okay, but can we tell the program to search for more combinations?
You need yes and no. That means that one, you can start with different starting geometries. That means that you can do more than one starting geometry, and in order to see if you converge to the same or not. Or you can do some dynamic approach, but when you do dynamic, that means that you give him some temperature and you let the atom moves. You're not doing quantum chemistry. You're not doing the same kind of calculation. And you don't to do a full energy potential search is really rare. So most of the time you will have to identify what is the minimum that you want, and to try to get a starting geometry that is around that.
Okay. So, and how we can start with this? How we can get this type of geometry to start in order to be right? Like, how we have to decide? We simply have to make some reasonable structures. So do we have some list of checkpoints in order to know if we have the reasonable structure?
It will be a point that we will discuss Friday, when you will have your compounds, and I will give you my opinion and share my experience. Okay, so first, the structure need to be quite reasonable. That means that if you put like 8 atoms or 7 atoms really close near to each other, you will be far from maybe, or even 2. That means if you put 2 carbons really near, you will be so high in energy that it will take really some time, but you will generate integrals with interactions that are really high in energy, and you can destabilize or even crash the system. It can happen, for example, if you forgot and you have 2 carbon in the same position. Usually the program will crash. Okay, because you will have internuclear interactions that are really strong, and it will crash the problem. So, the figure above describes the potential energy surface of ozone. Propose a way to calculate. So, to have this fully potential energy surface, you have either to block the geometry. That means that you will compute the grid of all the points, and you fix the geometry. So you don't let the program to change the atom position. You only do single points, and you optimize or you minimize the energy of all the geometry here. So it takes a lot of time. Or you do a dynamical approach, but for that usually it's molecular mechanics. And for example, if you tried, some of you have tried hyperchem or some, you can do some optimization rapidly, and it's more or less doing a VSEPR. That means that it will try to mimic classical organic chemistry, for example. When doing an optimization of this system, what will be the results and how does it work? So the answer is that I expected that you draw me the graph and you say, okay, so we minimize the energy and you will change the geometry until you reach the first nearest minimum. How can we... so it was in 2... I've cut the question. So how can we compute the transition state and check if it is really a transition state? What do you propose? So we have done, for example, we don't have the full energy surface, okay? But we want maybe we have already calculated, for example, the global minimum and the relative minimum, and we would like to compute the transition state to have the energy of the crossover barrier. What can we do? I can change the question is why sometimes when you launch your calculation you will not get a minimum, but you can converge to a transition state, and this is problematic.
Je peux répondre en français ou pas?
Oui.
C'est parce que ça va calculer les extrémums les plus proches, c'est ça? Enfin, c'était quelque chose du style.
So the answer of Arthur is that he's going for the extremum, and it's not the correct answer. That means that beware, it's not exactly that. Here, your transition state, for example, this point, is an extremum in one direction, and in all other direction it's a minimum. So that means that a transition state is almost a minimum minus one direction. And sometimes he is stuck there. Why? He cannot go from here or here. And the answer is that in the program there is an implicit condition that you've put, and sometimes you don't even know that you ask this question. So for what could be the reason that force the system to stay in this region?
When we ask to him to not change the length between the atoms.
Okay, so you can force you can force one coordinate, or no, one set of coordinates, or one bond length, for example, or one angle, but that means that you already know the answer of what you're looking for. That means that you know, for example, experimentally, or someone has already done a calculation, that if you set the distance here at 1 point, I don't know, 3, 4, it will correspond to a maximum of energy. When you do that, it is explicit in your input. That means it cannot be oh, I didn't know that it will not limit the optimization. No, it's more insidious. And George talked about it before, but it was not in this case, but the answer was already discussed in the course a little bit. No? The answer is when you force a point group symmetry. So for example, if you ask for a particle or some kind of axial, or the most typical approach is for a molecule. If you draw a planar molecule, Gaussian will detect that you have a planar molecule, so you have a symmetry plane, and it will force this element of symmetry. And if your minimization needs to break this symmetry element, it will be stuck in this point group symmetry. So it will not optimize to, for example, the global minima. And when you do that, sometimes you don't even realize that your compound has detected a point group symmetry, and okay. So here you will have in your case, if you have a planar system, it's by imposing the geometry. Here, by imposing the geometry, the most symmetric compound is this one, okay? So it will not be easy to explicitly force this compound. So you need to employ the method proposed by Arthur, is that you say at your program that he stop looking for a global minima and he start for searching for a transition state, a saddle point. That means it's a minimum in everything except one coordinate. That means that, and it works if you are only or almost already at for example an optimization. If you already have this optimization, or if you have already this optimization, or if you have both, you can tell the program, I have this geometry, they are both global minima. Between the two, what is the most important difference? So here it will be the distance between the two oxygen and the angle. It will try to go at the half, and it will try to do a maximum of energy. So the program indeed works with extremums of energy, usually a minimum, but if you want, and only if you know more or less between two minimum what is the maximum that you search, it can search for a peculiar extremum. That means that to calculate a transition state, either it is with symmetry and it's easy, you impose the symmetry, or it will be tricky, and that means that you need to compute, usually you need to compute both global minimum that are between the two, and to try to do, okay, let's start from the half and try to go slowly and to find the extremum of energy.
Okay, but you said that the computer can be stuck if we choose only one symmetry to search in. Yeah.
Yep.
Okay.
Unless you give explicitly the order to Gaussian, for example, to discard the symmetry property. And this is a keyword that is many times forgotten, because it can be interesting to use the symmetry to gain some time, because you can reduce, if you have a symmetry plane, you can reduce the number of orbitals and interactions by half. So it can be quite interesting. But if you see that you are stuck for this reason, you can break the symmetry, or you can say, okay, no symmetry, and you compute. And doing so, you will go normally to a global minimum. So the good question is, you think that you've asked correctly to optimize the ground state. How to check if we have the ground state? You do the frequencies calculation. So I'm searching for pictures. Usually I draw. I need to. Yeah, I know. Okay. So if we consider only a minima, a simple with just one coordinate. Usually it will be more than one coordinate. A global minimum will have only positive normal modes. That means that when you compute the vibrations of the molecule, you will only have positive frequencies, and that means that is reasonable. The energy of a compound is and the energy of a vibration depends on if you move the atom, it costs energy. But if you are here in the transition state, and if you move the atoms, those two oxygen, if they get nearer or farther, you will lose energy. That means that you will stabilize your compound because you are not in a global minimum, you are in a local extremum in just this direction, in the direction of this intrinsic reaction coordinate. If you move the atom, you will lose energy. That means that you will have a negative frequency. That means that if you do your optimization of your ground state, and if you do the frequency calculation, and you see that there is like 3 negative frequencies, something went wrong. You're far from a minimum. If you have 1 negative frequency, that means that you're not fully in a global minimum, and you are in a transition state between two states. If your frequency is really, really low in wave number, that means that you have, for example, two optimized states that are really near each other. It can be, for example, a methyl. If you move a little bit the methyl, it will be in another global minimum, but all those conformations are almost the same energy. So he will stop the convergence, and he say, okay, if I change it, it has a really low impact on energy. So I say stop. That means that I've made 100 geometries, and I cannot get a full global minimum. I'm finished. So second step, check the ground state, check the geometry with frequencies. If you have a negative frequency, that means that you are not in the most stable geometry. Your frequency depends on your position, and it depends on the first derivative of this energy, and that is why if you have a slope that is an extremum, when you move around the extremum, you will lose energy. Okay, that's why you have 1 negative frequency. Three vertical transitions. Maybe I will do that the other time. because I've done this part of class, but so today what we'll discuss is jazz. The excited states are not the energy minima. So we cannot compute the excited states with the same method. Our methods are made to minimize the energy, minimize the geometry if we ask. We can impose source symmetry, but we cannot say, okay, I want the first singlet with the lowest energy. So you need to calculate unstable states or unstable states or time dependent states. That means that they are states that have a short life periods. They exist mathematically, and you will take into account the normal, not the normal Schrödinger equation, but the time-dependent Schrödinger equation. Time-dependent, usually they are called TD. For example, and it works on already converged ground states. If you calculate the excited states of a non-relaxed ground state, you can have strange answers. So if you use DFT for ground state, you should use TD DFT for excitations. Okay, that's what we call coherent. That means that if you do, for example, Hartree-Fock for the ground state, you should do TD Hartree-Fock for the excited states. Or you use, and it's one of the other answers that I could have done to our team, maybe you can use some previous low-cost calculations to have a reasonable structure, and you can further converge with a more sophisticated approach based on a first simple approach. Okay, that means that, for example, okay, so this compound is quite huge. I will do a low-cost computational approach. If it seems reasonable, I use this geometry to go further with a better method. When you do that, it gives you vertical excitations. Okay, so perfect for absorption, mais pas pour and not for emission. And here, your Jablonski diagram is not correct. In your Jablonski diagram here, you don't have the S1 relaxed state. Here, you don't know if S1 is at the geometry of your ground state or not. So if I come back to here, up, up, so here you have the global minimum of your ground state. And when you do the absorption spectra, vertical excitation, you go here. That means that you go to an excited state 1, okay, but is not at the lowest geometry. Let's take an example. You have a pi compound, okay, and your first excitation is one double bond that goes from a pi orbital to a pi star. That means that when you excite the compound, you will break in part the double bond. That means that if you leave this excitation enough time, the distance between the two carbons will change, and this will reduce the anti-bonding interaction. So you will minimize the energy of your excited state. This is the case here because the first excited state, E1, okay, if you change the geometry, you will stabilize the compound. And if you let the time to stabilize, when he's stuck at this excited states, and if he cannot do vibrational relaxation anymore, he will emit a photon, and the emission wavelength will be a vertical one and go straight to the ground state at the state 1 geometry. So here you have an excited state 1 that is not fully relaxed, and when you emit, you obtain a ground state that is not fully relaxed because it has the same geometry of the excited state 1. And the difference between the two arrows is the stock shift. That is why you've learned that if your stock shift is quite small, for example, it can be deduced to a structural property that is a rigid compound, for example. That means that if you go to an excited state, it will emit with a wavelength that is quite near the absorption, because the excited state is stable with the same geometry as the ground state. If you have a large stock shift, that means that you have a large geometrical rearrangement, and that means that the structure is not rigid. It can easily change the geometry to adapt to a new geometry of the excited state. So when you do the vertical transition, you have the process of absorption and emission. But for emission, you need the excited state minimization, geometry minimization. And this part is quite tricky. To minimize an excited state is quite complex. Because if you are here, and if you want to go here, you cannot just ask the program to go up in energy and find a minimum. So you need to get this information. The problem is that you are not here. When you do the TDDFT, you are here. That means that you have this energy and you compute the absorption properties. And when you are here, your absorption property is your emission. But you are always working in the ground state. Because if you are here, the calculation will automatically go down in energy, because you have one state here that is theoretically much more stable. So what we do is we try to minimize this kind of energy. That means that you have here an energy that is higher, and what we minimize is the difference of energy between the two states. Sorry. So here, what we will look at minimization is not the total energy, but you will try to minimize the emission energy. And that will allow for the estimation of the emission properties. Okay? So next Friday we will work. You will present to me what are your problematic, or what you think about your problematic. So if you can present a PowerPoint or an article or something, a sketch or something like that, if you can prepare your molecules, drawing of your molecule with ChemDraw, or even if you already have the Gaussian and other program, okay, and we will try to get the input done. I will try to walk you through what are the keywords that you need to give to the computer to be able to get an answer. We will launch the calculations, and we will continue with a little bit of theory of what are the calculations results and what to expect, and it will be enough for Friday afternoon. Thank you to have checked in. I will